Alright, so we should first talk about what this module structure is, because it's just an example that they use in the text, and I don't think it's something that comes up a lot. At least it hasn't yet. I think there were some hints or some foreshadowing in the chapter that it might be useful for some algebra stuff later on. But like when I took classes and we covered modules and stuff, this never really came up. So I'm guessing this is just, at least for now, it's just like a example. So let's recall that if t v to v is linear, i.e. it's a linear transformation on v, then our f lambda module v will satisfy, so here we take a polynomial a0 plus a1 lambda all the way up to am lambda to the m, applying x to this. I guess I'm going to have to, or I can just do this. This is equal to, we just take a0x plus a1, and then we apply t once to x, plus all the way up to am, then t apply m times to x. So you basically, you replace lambda to the I with t to the I x. That's all that's happening here. And of course t to the 0 x is just x in this. So yeah, that's just a module, and we prove that's a module and everything. So we have this linear transformation. I'm not going to prove it's linear because it's obvious and I don't feel like it. And so we know that, okay, obviously R is a field F, so we're using capital F. We're using capital R in place of capital F here, so that's fine. So let's prove A, B, and C. So then lambda x, what is this? This is just t of x, which is obviously xn, x1, up to xn minus 1. Okay, so that's that. Now this next one, we have lambda squared plus 2x. The lambda squared is going to become t squared x. And what is here? I'll just write out t squared x plus 2, and then this is just going to become 2x. And so this is t squared x is, we're going to apply at t twice. So instead of starting with xn, we're going to start with xn minus 1, then go to xn, then 1, 2, all the way up through xn minus 2. This is plus 2x1 through 2xn. That, of course, is equal to xn minus 1 plus 2x1, xn plus 2x2, x1 plus 2x3, all the way up through xn minus 2 plus 2xn. So far these are just like not very illuminating. It's just like, hopefully through doing all these, you actually, by writing this out, you actually are forced to memorize what this action is. And then this last one is a little interesting because we have lambda n minus 1 all the way up through 1x, reducing in powers. So what is this going to be? This is going to be, so the 1 is going to give us x. The lambda is going to give us tx. Lambda squared is going to give us t squared x, all the way up through t to the n minus 1x. And what is this going to be equal? So if we look at the first look, what is each of these terms going to contribute to the first entry? This x, obviously, we're just going to get xn, or x1. For tx, we're going to get xn. For t squared x, we're going to get xn minus 1. So we're starting at 1, then we go to n, and then we keep decreasing. And where are we going to stop? We're going to stop at t to the n minus 1. Well, t to the n minus 1, this is going to go... So let's see, we got x1 plus xn plus xn minus 1 all the way up through... And then we got the first entry of t to the n minus 1x. Now, because this is... Let's see here. Because this is a permutation of n letters, its order is going to be equal to... Like, if you do it n times, you're going to get back to where you started. And so... if we stopped at t to the nx, then we would be back at x1. So this is obviously, so we start at, so it's going to be like the very last thing before we get back to 1. So it's going to be x2, because we want x1 and n minus 1 counting all the way down to 2, and just before getting back to 1. And so this is just the sum from 1 to n of xi. Okay, so that's first entry. But then the second entry is just going to, instead of starting at x1, we're going to start at x2, then we're going to go to x1, then we're going to go to xn minus 1, and then we're going to stop at x3. And so again, we get sum from 1 through n of xi, and obviously this pattern continues. So every entry is the same, it's just the sum of all the xi's. Okay, so lastly, we want to figure out which elements satisfy this equation, lambda squared minus 1x equals 0. So let's compute it and start with that. So this is very much like this other example we had. So this is going to be xn minus 1, xn, x1, all the way up through xn minus 2, minus x1 through xn. So this is, so here we have xn minus 1 minus x1. We have xn minus x2, x1 minus x3, all the way up through xn minus 2 minus xn. Now observe that the value xk, or the symbol xk, appears in entries. Well, which entries does it appear in? In the second term here, this minus x, it's obviously going to be in k. But in the first one, it's k plus 2, but we allow it to shift. Like it can loop back around. So in entries k and, well, how do we write down that looping back around? That's just k plus 2, but we loop back mod n. And this, so yeah. Okay, so then that's really important because now suppose lambda squared minus 1x equals 0. We want to figure out which elements of x will satisfy this. Now, if n is even, then x1 equals x3 equals all the way through xn minus 1, right? Because, let's see here, if n is even, then n minus 1 is odd, and so we're starting at x1 and counting up by 2's, and we're going to end at the odd number xn minus 1. And then the next thing after this will be, you take n minus 1 and you add 2, and that'll give you n plus 1, but then you take that mod n, and that gives you back to x1. And so we just loop back around again. And, okay, so that's for x1. What about the others? We have x2 equals x4 plus, and then this is going to go all the way up to xn because xn is even. Of course, this is counting even numbers. And when this loops back around, it becomes xn plus 2, which mod n is just x2. So lambda squared minus 1x equals 0 if and only if here I'm going to have to scroll up. If and only if the odd and even entries. Here, let's say it this way. If and only if the value of if and only if all the odd entries and all the even entries of x are equal. I paused a little bit there because it's just a strange thing in English that I'm trying to think of a clear way to write this, because you want to write that all of the odd entries of x are equal to each other, and all of the even entries of x are equal to each other, but the value that all the even ones take need not be the value that all the odd ones take. And writing it like this, it makes it a little bit ambiguous. You might interpret this as being all of the entries are equal, but that's not the case. I could write that out in a little more detail, but I'm not going to because I just explained it. And so hopefully my explanation gets rid of any ambiguity in this phrasing. Okay. So that's if n is even. If n is odd, then x1 equals x3 equals all the way up through xn, and then we go, and why do we go up to xn? This is because n is odd, and so we're going to end at xn. But then we're going to go to xn plus 2, but that mod n is x2. Then from here we're going to go to x4, and this is going to lead us all the way up to xn minus 1. And so all of the values are equal. All of the entries are equal. So lambda squared minus 1x equals 0 if and only if all entries of x are equal. And I guess I didn't, I forgot to say this, but it should be pretty clear from our from the formula that we got for lambda squared minus 1x, that if two things appear, because it's like blank minus blank, blank minus blank, every entry is of the form blank minus blank. So if two elements appear in the same index, then they must be equal. So here x1 minus x3 is one of the entries, and so if lambda squared minus 1x is 0, then in particular this entry is 0, which means x1 minus x3 is 0, which means x1 equals x3. So you can tell that two entries are equal. You can tell that xi and xj are equal if they appear in the same entry of this vector lambda squared minus 1x. And then you just kind of go from there and you see all the possible ones that's in. So you see like here, like x1 is in the first one and the third one. So that tells you that, okay, the first entry tells you that x1 is equal to xn minus 1. Then the third one tells you that x1 is equal to x3. And then you just go from there. Probably should have explained that first, but that should illuminate, if it wasn't clear already, why everything else is kind of straightforward. And so there we go. This completes this exercise.